First, let me thank the organizer for the nice conference, and I've been learning a lot in these days. It's a pity that the conference was online, but unfortunately timing was coincided with this home complete. So today I'm going to talk about the topic that was discussed already in 2 talks in this workshop, first by Zohar, and indeed is work in progress with Zohar, Mark Mezei, and Gabriel Cuomo. And also there will be some overlap with the talk of Professor Zitlin, but I think it's a good thing so that we can present somewhat complementary perspective. So, okay, as you guessed from the title, the talk will be about line defects in physics, in particular line defects in conformal field theories. Many examples have been mentioned. For today, it will be important to mention magnetic impurities in lattice systems, so in condensed matter systems. And I want to remark that this can be an interesting topic even if you're not interested in condensed matter, because these share a lot of similarities with Wilson and Tooth lines in 4-dimensional conformal gauge theories. And today I'll discuss, as the title says, some semiclassical links. So roughly speaking, my talk will be divided in 2 parts. The first part will be about impurities, as I said. So what's an impurity? You take some lattice system, say in 2+1 dimension, and you place one of the atoms with a doping atom of a different spin. And that's a line defect because it's extended in time, and it will couple to the bulk with a localized coupling like this. And it's clear that in the limit in which the spin of the impurity becomes very large, so it's in a free system, this will act as a large source, and therefore you might expect some sort of semiclassical description. The second part of the talk instead will deal with Wilson lines, large representation in conformal and mostly superconformal gauge theories, but I've tried to have some at least speculative general comments. And I'll argue that the ideas that we will develop for the case of the impurity will kind of translate or be inspire us in the problem of the Wilson line. So that's more in detail the plan of my talk. So as I said, I'll start with impurities. I'll mostly discuss the case of a free bulk at the beginning, but I'll try to quickly mention the highlights of our result for the Wilson-Fisher free model. And then I'll have some general comments on Wilson lines, and I'll provide for you an effective field theory describing Wilson lines in large representation or alpha VPS lines large representation in n equal to superconformal field theories, and I'll check my results against localization ones whenever available. So let's start from impurities. So the problem of impurities is relatively simple. You start with a O3 vector model in the bulk, and that model, this is your lattice system. We'll take D arbitrary, even so for some time I'll take it close to 4, but not always. And some potential which models the interaction, and it can be either free or quartic or something more complicated, but for this talk I will just focus on these things because I have a unique bulk field. And I'm tuning a master to 0 because I want to be at the critical point. How do you model a spinous impurity in such a system? It's relatively easy. A spinous impurity has 2s+1 degrees of freedom according to the representation. So you just have to couple the bulk scalar field to some matrix in the appropriate representation of SU2 and integrate over the line because you want to have effectively 1-dimensional defect. There is an arbitrary coupling, a trace, and a path ordering pretty much like in standard Wilson lines. So this is a simple problem at equivalent for Wilson line in technical sense. So let's start discussing the free bulk case. So of course this is a well-known system studied in the literature, and it's quite non-trivial because when you expand perturbatively, you have the path ordering, so you have tons of commutators to take, and even though it's a free theory, it turns out this model is not solvable. In fact, it's quite rich. People studied in the epsilon expansion long ago, around 20 years ago, Sachdev and Sengupta, among others, and found, by standard analysis and Wilson-Fisher fixed point, and did perturbative analysis of this model, which you can always do. And you can also compute other quantities. For instance, you can compute the partition function when you place the defect on a circle. This is of somewhat theoretical interest because it's proven to decrease under defect energy flow, but you can check this. But now what happens as you take the large spin limit? So what happens once this matrix T becomes huge? Well, let's try to check this by computing the partition function again for a circular defect of concreteness. You expand your exponential as a sum and you start doing Greek contractions. Leading order, you find something goes like gamma squared trace t squared, and since t squared goes is ss plus 1, it's just SU2 Casimir, this case like gamma squared s to the cube. There is a factor from the trace. Subleading order, you find something which goes like the coupling to the fourth power and s to the fifth by the same argument. And just roughly counting, not computing. And so forth, so on, then gamma 6 s to the 7. So you might be tempted to conjecture. So first you see that higher and higher orders have higher powers of s. So perturbation theories cannot be trusted in the largest limit. You might be tempted to conjecture that you need S gamma, that when S gamma becomes of order 1, perturbation theory breaks down. But that would be slightly too quick. If you start honestly computing, you find something somewhat miraculously that many terms exponentiate. And the result eventually up to a prefactor, which is the free theory G function, just takes the form of exponential of a sum of over loop order n, gamma to the 2n, and polynomial of order n plus 1 in S. So diagrammatically, this is very unclear. So from this formula, you immediately conclude that perturbation theory breaks down nonetheless when S is too large, but it happens a bit later than you might have expected. It happens when gamma square S becomes of order 1 or 4 pi square if you restore your 4 biology. But still, this formula and it's reminiscent of similar formulas in other contexts and suggests that if you start grouping leading terms all together, so the gamma to n Sn plus 1 term, and similarly for the subleading term, you can formally recast the expansion in this way. So as a series at large S and p gamma square S. Of course, this is just formal because at this stage f minus 1 and naught are just sum of infinitely many Feynman diagrams. So there is no physics. But this suggests, could there be some physics? Could we compute right away these functions in a novel way? And the point of my talk is that yes, it can be done. And the key idea is similar to some prior works in the context of multi-layer damping. In fact, I should have mentioned here works by Rubakov and Son in the 90s and some recent context in the epsilon expansion, this work that we done recently with Gilles Bader, Sasha Moy, Riccardo Rattazzi, and is to expand the path integral around a suitable trajectory that resums this gamma square S series for you. So the way this is done was already, I think, mentioned by Professor Zittel in this talk, but let me remind you or present you an alternative way, in fact. So the idea is that you can represent the defect now, the quantum mechanics of the defect, by using some action. And there is an obvious action, or there are many possibilities, but a simple one is to use a bosonic bispinor Z, which is constrained and has a U1 gauge symmetry. So whose kinetic term is Z bar Z dot. This has a U1 gauge symmetry because if you make a U1 shift, you get a constant times a total derivative. So the constraint and the U1 gauge symmetry make the Hilbert space finite dimensional, is a non-coadjoint orbit, or maybe you know about it. And the spin operator in this language is represented as a bilinear in the field Z and couples to phi in the way you expect. And okay, in condensed matter literature, this is exactly equivalent to the path integral for a charged particle in a monopole on the sphere, in the lowest non-low level. So once you have an action, it's obvious how to do semiclassics. You just rescale your fields to see what's the right semiclassical limits with the power of the large S, so square root of S. You get that the defect, the path integral is just 1 over gamma square times an action which depends purely on gamma square S. So you can clearly just compute your path integral by saddle point, and you will find your G function, or whatever other observable you want to compute, in a double expansion at large S and p gamma square S indeed. So this, okay, is already what was said a few days ago, but a non-trivial point that I want to highlight is that this saddle point, turns out, works also for D close to 3. So it allows us also to solve dimension D equal 3. In this case, the interpretation of gamma square S is not that of atomic coupling, it's rather a bit more like a mass terms or for a non-local quantum mechanics. I don't have time to explain that in detail, But plausibility argument for why this is true is that the largest limit in this case looks pretty much like in the large N limit of the M model, where we know we can solve the full flow in a 1/n expansion. And this is special of the free theory, of course. It won't apply in the bulk interacting case. As an illustration of this general argument, let me just say that, okay, this is free theory, so the saddle point is remarkably simple. It's just phi is proportional to the spin operator times 1/d minus 3, where r is the distance from the defect. And the spin operator is expanded around a constant background. Now, this saddle point cannot break the SU2 symmetry, so this just means that there must be some zero mode in the path integral which restores it. So, in other words, we have a family of saddle points related by a global action or a finite dimensional integral that we have to take into account at the end, like standard distance. So the only result I want to show you for the free theory concerns the French diagram. So I told you before there was a unique infrared stable fixed point in the epsilon expansion of standard fixed S. But here you find a remarkably richer phase diagram. So you call alpha your suitably rescaled coupling, so that is fixed in this limit, and you find this beta function for leading order 1/s. And so here I plot the beta function times S as a function of alpha in different regimes. For in epsilon equals 0, so in equal force, strictly speaking, this beta function doesn't have any non-trivial 0 besides the stable 1 at alpha equals 0. So the coupling is marginally irrelevant. As soon as we go to epsilon between 1/pi, epsilon s 1/pi, and epsilon s equals 0, we find two fixed points. This one is just the simple continuation to this regime of the fixed point I discussed before. But we also find a new one that at small epsilon s corresponds to alpha order 1/epsilon s. So it's non-perturbative in the standard approach. This fixed point is unstable towards the one that I mentioned before on the left, and on the right is unstable towards strong coupling. The two fixed points merge at epsilon s equal 1/pi, and eventually for epsilon s larger than 1/pi, so here I plot for instance per root of 2/pi, there is no fixed point. So in particular, what happens for epsilon equal 1, so in D equal 3, what's the fate of the theory in that case? And you can argue that in fact this beta function is reliable also in that case, and here the RG flow never terminates. So what does this mean? That's something that somehow sound unusual, but in fact we know many examples of defects, well, a few examples of such solvable defects when this happens, and they all involve free theories or modular spaces. It just means that correlation functions at finite distance from the defects, like one-point function, they will still decay, but they will decay with a power law which is somewhat slower or smaller, if you want, than the one that you would expect in a defect conformal field theory. So in defect conformal field theory, one-point function will decay with powers of the scaling dimension of the field. Here, the power will be smaller. So that's all it means. And yeah, so in particular, we conjecture that also for S order 1, there is no fixed point directly in D equal 3. And in fact, this is somewhat in agreement with some recent bootstrap result that tells us that there is no interacting fixed point in 3 dimensions for free large scalar field, no interacting defect conformal field theory in D equal 3 for free scalar fields. Okay, so this was for the free theory. Let me now quickly mention the generalization to the interbulk interacting case. This is a case of interest in physical materials because it describes magnets, of course. The stuff is the same, it's the same defect, it just changed the potential. You can study in the epsilon expansion. It turns out that in this case, if you perform the semiclassical analysis, there is no new fixed point for all values of S. The fixed point is still the same, even at large S. But nonetheless, its study for large S cannot be performed by diagrammatic perturbation theory. You need some resummation, pretty much like before. And here, I don't want to give you, I won't explain how we obtain this result, but the highlight is the following, is that in the largest limit, we can argue that the impurity dynamics completely decouples up to SU2 zero mode. So what does this mean? This means that in the S to infinity limit, and this holds for arbitrary dimension D, so also in D equal 3, there is an equivalence between the impurity problem and the problem which is different up to this zero-dimensional integral. and you can check this in the Epsilon expansion. So what is this problem which is different? This problem is the problem that you obtain by adding to the free model a perturbation in a certain direction and of the field space localized on a line. So it's like adding a magnetic field localized on a line. This is called sometimes pinning field in the condensed matter literature. In this setup, you can interpret this magnetic field as a relevant fixed coupling on the defect. And this means that under RG, this will lead to a non-trivial defect CFT in the infrared, so non-trivial defect conformal fixed point. Here the flows does stop. And also you have some exact results based on word identities because this system breaks explicitly the symmetry. Of course, the impurity doesn't because you have this zero mode integral. But at leading order in S, you can relate the spectrum of the two, and this does break the symmetry, so you have some exact equivalence. And in fact, we have a lot of data about this problem based on some Monte Carlo and based on our recent paper. And we can also compute one of S corrections systematically in terms of absolutely CFT data and check in the Epsilon expansion that their calculations are correct. So the main message I want to convey is that this large S limit allows to make physical prediction also for impurity in the equal free and interacting case, even though it comes in a somewhat more subtle way. Okay, so I think that's it for the impurity. And if there are no questions, I'll now jump to Wilson lines. So, okay, the problem of a Wilson line we all know. So let me take for concrete as an abstract SU2 conformal gauge theory. Could be a gauge theory something like 5 value fermions in the joint, which is believed to be in the conformal window. And now, the Wilson line, at least in perturbative theories, we know how to write it. And it's precisely the same thing that we had there for the scalar, just with a gauge field. And okay, we expect that such Wilson lines defines a well-defined conformal defect for all values of S. That's because there is no running coupling up front, and we, in the examples we know, we don't know relevant perturbations of Wilson lines. I don't know if I have a very well non-perturbative argument away from the superconformal limit. Another point which is convenient is that it's useful to think of this problem not in flat space, but on ADS2 times S2. So for conformal field theory, this doesn't make any difference, of course, because this is just a variable scaling of the flat metric. Sorry, there should be a capital R here. And the metric in some coordinate looks like this. This is the sphere metric, and this is the ADS2 metric. And R is the radius of both the ADS2 and the sphere. The radius must be the same, otherwise it's not conformal equivalent to flat space. And the reason why it's convenient to do this is because by the defect version of the state operator correspondence, the spectrum for the theory quantized on this manifold, or more precisely the spectrum of boundary condition in ADS2 and times S2, is equivalent to the spectrum of operators on the defect. And I should say in this geometry, the defect lies at R equals 0, so the boundary of ADS2. You can think of that as the boundary conditions. So, okay, here I could, Professor Sitrin performed a nice analysis of this problem a few days ago, and I could try to perform a general analysis on some model. But I want to be slightly, to try to take some general conclusion by generalizing what we learned before on the impurity. So we do have a path integral, and by the same technology, this path integral can be written as a defect conformal field theory action, integrated over the bulk fields, and impurity field or defect field that is just representing the color degrees of freedom on the Wilson line, something well known. In the limit where the representation is much larger than 1, we might naturally expect, by generalizing what we learned before, some semi-classical trajectory to dominate this path integral. And this trajectory will inevitably set some massive scale on the manifold that I mentioned before. In particular, the massive scale will be constant. It's associated with the electric field. So this trajectory will have a large Coulomb field, or more precisely, will have a family of trajectory averaged over the color. And each of them will have a large Coulomb field and correspondingly a large gauge field. And this large electric field will naturally set an hierarchy between this mass scale and the compactification scale of the manifold. And in presence of such hierarchies, we are used to think that there must be some effective field theory description. Okay, so now I could go on and construct a general effective field theory description. So one way to motivate, for instance, if one more clearly, is that consider two lines, because I think it's kind of equivalent in Euclidean, but it's simpler. We know that particles, the magnetic field, organize in Landau levels, and Landau levels have a natural gap, which is the cyclotron frequency. So you might expect you can integrate out massive charged particles. You can integrate out charged particles because of this Landau level thing. But rather than doing that, I want to focus on a case we understand better, which is a case where we have additional symmetries, which is namely superconformal field theories. And the main reason for doing that is that there I'll be able to check non-perturbatively the prediction of the effective field theory. So let me do that. In this case, the setup is almost the same, with the difference that now I'll take half APS loops. And I'll take n equal 2 or bigger. And I'm only talking about four dimensions, of course. In this case, in Lagrangian theories, we know that our BPS lines are represented as a generalization of the Wilson-Maldacena line, just in an arbitrary representation, and contain both the vector and the scalar component of the vector multiplet. Something perhaps less surprising is that all BPS lines have a notion of gate charge and exist also for non-Lagrangian theories. Roughly speaking, you can in class S construction theories, there is a geometric engineering way to build them, but one way to think of this is that you can represent them in the Coulomb branch, and you can label them through their electric, magnetic, or the ionic charges in the Coulomb branch. You can classify which one exists based on consistency, and then once you have a bunch in the Coulomb branch, you can construct all others by the OP. It's non-singular for superconformal lines. So there is a large gate charge limit also for lines in non-Lagrangian theories. The main difference here with respect to the general discussion before is that you will source both a large scalar and a large vector field, both a Coulomb potential and a scalar field, of course, because of this representation. And we know that in theories that have moduli spaces, states which are dominated by smooth and huge scalar profiles are naturally described by the moduli space EFT. So, okay, here I could make a kinematic argument and construct the most general EFT, but it turns out, and it's physically obvious, that the only possible EFT in this setup coincides with the Coulomb branch effective field theory that was classified for us long ago by Seiberg and Witten, but in fact probably also before in the conformal case. So the effective field theory is naturally organized in a derivative expansion 1 over S squared. It has a kinetic term, a West-Zumino term, or proper symmetrization, of course, and further terms which are D terms. So the kinetic terms scale like S squared. And as you know, it only depends on a unique coupling up front. And these are the relevant parts. It coincides with a scalar, the gauge field, and then fermions, and possibly hypers that might appear in some superconformal field theories. Like in n equal 4, we must have an hyper just to have n equal 4 supersymmetry. The West-Zumino term is the most interesting one because it has an anomalous scaling. All terms in the effective field theory scale like some power of S, but the West-Zumino term is associated with the Weyl anomaly. So it scales like with log S. That's because the scalar fields on the saddle point, I showed it before, scale like S. And therefore, the West-Zumino term contains a logarithm of the dilaton, which is equivalent to logarithm of the scalar field, and therefore has some log S scaling. The coefficient of the West-Zumino term is also known. It just comes from Weyl anomaly matching. And it's AUV minus AIR. And what is AUV? AUV is the Weyl anomaly coefficient of the UV CFT, so the full model. And AIR is instead the Weyl anomaly coefficient of the Coulomb branch fields. So these coefficients are known for all n equal 2 superconformal field theories of rank 1. I'm only talking about rank 1, I should have said that. And there are, of course, other terms, but they won't be important, and I'm not showing them. But of course, there is a well-known supersymmetrization, which is the Dunning-Seiberg term. Another important point is that only the kinetic term and the West-Zumino term are F terms. So only these terms contribute to supersymmetric observables, like expectation value of the up BPS loops. All the other terms are D terms, so they won't contribute to supersymmetric observable that will be important for non-supersymmetric observables that you can also compute. So like correlation function of a long multiplet in the presence of the line is a non-supersymmetric observable, for instance, and you can compute it. The Wilson loop is obviously represented in the obvious way. Formally, you should represent it to its representation on the Coulomb branch, which is classified for these lines. But the only components which gives a non-suppressed contribution are the highest weight, essentially. So I think it's quite intuitive that you represent as sum of a billion lines of charge S and charge minus S in the most generic case. But it's straightforward to generalize to non-generic case. Okay, now we have essentially an effective field theory is almost a free model with some tiny correction. We can just compute. We expand around the saddle point. Saddle point, again, is simple. You see both the gauge field and the scalar field scale like S, and I kept the contour of the line arbitrary for simplicity, for generality. And here I want to just show you results for protected observables, because those can be matched to supersymmetry. So the expectation value of the line on a circle is called G. It is a well-known formula due to Peston and others. In this case, like S squared times the infrared gauge coupling, which is a Wilson coefficient. And then it has a very interesting log S correction, which depends on these anomaly coefficients I mentioned before, and stability. Additionally, another supersymmetric observable is the expectation value of the stress tensor in the presence of the line. It's fully fixed by a unique coefficient HD. And we found that up to some order in S, in fact, we conjecture up to exponentially small correction in S, it's related in a very nice way to this log G here. So there is an interesting relation which you can prove through effective field theory. And the reason why I'm telling you of this is that, of course, for n equal 4 and n equal 2 with 4 Fermis in the fundamental, for instance, and we can explicitly check these predictions against exact result from localization, even at strong coupling, and we find perfect matching in the largest limit. And for non-Lagrangian theories, as there is these equations here are predictions instead, and they're harder to check from localization. Some cases probably possible, but you know, based on the agreement that we had in all the cases we could study from localization, we believe they're correct. Let me also mention that this story is remarkably similar to another story developed by LM and collaborators in the past years. Okay, so I think this concluded all I wanted to say. So let me just summarize the main message of my talk. I argue that there are some nice semiclassical limits for Wilson lines and impurities, and they are remarkably similar. And for the impurity, I think the highlights are that semiclassics allow overcoming some breakdown of perturbation theory when the spin becomes large. And perhaps even more importantly, we have prediction for physical impurity in 3D for magnets. For Wilson lines, I instead motivated the idea that there should be an effective field theory description for large representations. And I studied in detail the case of superconformal field theories, found in perfect agreement with localization. The outlook is, of course, is rather broad. I mean, for impurities, there are more models to study, and most importantly, comparison with simulations and experiments. For the Wilson line problem, we want to study, of course, more perturbative theories, possibly in a double scale limit similar to the one that I described for impurities. And in fact, this was already partially done in the superconformal case by Professor Sidley and collaborators at UARD, and as I also found out that day with you. But there are also the question about non-superconformal field theories that are Bang-Zach's fixed point that I think in principle are amenable to this treatment as well. Perhaps the most intriguing question concerns the connection between this effective field theory idea and semiclassical ideas with integrability and SCGP. So these saddle points we find in standard gauge theory probably should correspond to some geometries with large Berkeley reaction from the D-brane or something. It would be nice to make this comment precise in that context. That's all. Thank you.
Thank you, Gabriel, for being on time. So, are there any questions? We have time for questions.
Okay, maybe just a comment. I mean, for n equals 4, I mean, there is some fully back-reacted geometries that actually compute this H quantity that you were talking about and seem to reproduce the matrix models. I mean, you seem to reproduce the localization computation. Yeah. This H, yeah, this HD can be computed from supergravity in the large representation approximation.
Yeah.
Shota, I think, was the next.
I just wanted to ask a question about the superconformal, the Wilson lines in superconformal case. Like, do you have any predictions about like a defect CFT data from the effective field theory?
You mean like the spectrum?
Yeah, the spectrum, structure constants.
Yes, I mean, it's very easy to compute. I mean, so the spectrum to leading order, you know, it's almost follows immediately from the fact that the action is essentially free. Structure constants from, for say, long multiplets, they are computed up to some new Wilson coefficient. So to represent the long multiplet in the effective field theory, and there is some Wilson coefficient in the matching. But up to you can predict the scaling with S, for instance, of this 1-point function, higher point functions in the bulk.
I see. Yeah, at least in the case of n equals 4 supermills, like there is some like interesting sector, like in which the structure constants can be computed from localization, but it depends non-trivially on the coupling constant. So I was wondering, like,
so you're saying, so to be honest, we studied only HD or long multiplets. So yeah,
no, it's actually
there's much richness in between that that can be explored. I agree.
I see. Okay, thanks.
Grisha Kravchensky.
Yeah. Could you show, please, just previous slide, the slide which you had before this one, with it was almost next before conclusion.
This one.
Yeah. My question is, to me, it looks strange that this formula doesn't have term union S.
Okay. No, I mean, that's a good point. No, there is no term linear in S for sure. In fact, we see it in localization. I think,
well,
you know,
I could tell you why it should be there, because the argument is quite simple, that this formula should depend only on the Casimirs of the gauge group. In the Casimirs, even if you go to large spin limit, they have this fine symmetry when you replace S by minus S minus 1. So your formula, even though they found in large S limit, they should respect that symmetry. And this term S square obviously does not.
No, okay, I see the question. There is something funny which happens in the transition from the smallest limit and the largest limit. So in the smallest limit.
No, I'm taking largest limit. Just think about the largest limit.
No, but I'm saying in the smallest limit, for instance, you know, the G function, you're right, there will be an SS plus 1 there. But in the largest limit, this somehow disappears. I mean, if let me just think how that happened. Let me just think how that happened. Yeah, so I see. Okay, I don't have a good answer. I mean, I remember when we started, I also thought that the S of the effective field theory could not be the S of the representation because of this reason you're mentioning. But then we did the localization calculation, and we saw that S was really S. If you want, you know, S a priori, you might wonder here. So whenever I write the Wilson line here, you might tell me why this S that I put here in the effective field theory should exactly correspond to the S of the size of the representation. Why not S plus 1? It may happen. It's a matching formula at low energy. But it turns out that by comparing with localization calculations, that's precisely what is needed and what matches the exact result.
I think the intuition that that Grisha is bringing up is maybe in the planar limit, not for SU2.
No.
I don't think.
Actually, one of the reasons why I brought this issue, because a similar story happens. Okay, there is some parallel story which goes on with the anomalous dimension for large spin when you're dealing with representation of SL2. So
Yeah,
the same
for
argument.
the spin is true. For the spin, I understand that. I know. I think.
let me ask differently, that if whatever doing calculation you're doing, you're expecting your final result to be function of the Casimir gauge group. There is no question about that. So if it's question, it's function of the Casimir, unless you're dealing with U, not SU, but U unitary group, then I understand. But if it's the SU group, then there is no way you could get rid from additional terms which will be linear in S. I don't know any Casimirs which don't have subleading corrections.
No, I understand you. I understand. So I totally understand the question. I admittedly, yeah, it's a bit embarrassing. We thought about it, but somehow we were. I mean, from the effective field theory viewpoint, again, you can slightly correct the S here to say call this S tilde to S plus 1/2 or something, and then hope that and this will fix the problem to the order I'm showing my formulas, and then subleading orders can be fixed accordingly. So there is, in the effective field theory, you can match what you're saying. But then if you compare this procedure with localization, it doesn't work. So now localization is a 1D integral. So it's not like, it's not an exotic calculation. So it's, yeah, I don't have a smarter comment than that. I'm just saying, what you're saying could be easily accounted for in the effective field theory, but it doesn't seem to match localization. Now I'm confused what is technically happening. I'm sorry.
Okay. Well, thanks.
Okay, so it looks we don't have any more questions. So then we have a break for 15 minutes till, and let's restart at 11:20 the discussion.